In this video we're going to start looking at the idea of curl. Now in the previous video we introduced the idea of circulation. The circulation was the line integral around a closed loop of a vector function, and we took the dot product of the vector function and the tangential component only of that function. So we noted that there are certain situations where the value of this integral is path independent, meaning that it doesn't matter what path you take between 2 points, all that matters is the actual endpoints themselves, and those are the things that determine the value of this integral. So in that instance there, we can write that this line integral around a closed loop is equal to 0. Now what we want to do is we want to look and find this value of circulation, but we want to look at the circulation rather around this than around this closed loop. We want to try and think about the circulation at a point. So the idea of curl really is the idea of looking at the circulation at a point. So let's draw out our coordinate axes. So we've got x, y and z axes, and we've got our components I, j and k in those directions. I've picked some small volume element, and the top surface I've showed you in yellow. So the top and bottom surface make a pair, okay, and we've said see the right hand surface is in blue, so the right and left hand surfaces make a pair, and we've also got a little pink one at the front there, so the front and the back surface make a pair. So if we start off, imagine looking from the top down, so we're looking down onto this yellow surface. So the yellow surface is going to be sitting in the xy plane, so I've just drawn that down here. So we've got our xy plane and we've got our little closed loop. Now I've called these CR for the right hand curve, although it's not a curve, it's just a straight line. So it's CR for the right hand and then the left hand, and then you've got a top and a bottom, and we're going round in this direction here. Okay, now the central point here is just our point XYZ, and we know that the length of this line here is going to be delta x, and the length of the line there is going to be delta y. So if we multiply delta x, delta y, we get the small area inside, which we call delta s. Now we can approximate this line integral by taking the value of the function at the central point of the line and then multiplying it by the length of the line. So let's just do that here. Now I've written out this out in full. Okay, so this line integral here, it's a vector function. So the vector function is a component in the I direction of the fx value of the function xyz, and a component in the j direction of the fy component of xyz, and a component in the k direction of the vector function, the z component of the function xyz. And we're doing a dot product of that with the tangential component. Now the tangential component we've seen derived before was going to be I dx by ds plus j dy by ds plus k dz by s all times ds. So now we're interested in the line integral along this bottom face here. Okay, so the bottom line here, that's CB. But the only component tangential to this line CB is going to be in the I direction. Okay, so we can see then that there is no j tangential component, there is no k tangential component, there's only the I tangential component. So whenever we take the dot product with the I, well, I dot I will leave us with our fx value of the function, I dot j will disappear, and I dot k will disappear. So it means that this line integral along this line CB will give us only the x component of this vector field, and then we do the approximation. We take the x component of the vector field halfway along the line and then multiply it by the length of the line. So halfway along the line, it's just going to be we've got to come along x, and we've got to come up y to get to the centre, but then we've got to take minus delta y up and 2 off to get to that point, and the point z is the same, and then we've got to multiply that by delta x. Now we can do the same for the top line. The only difference with the top line is that we're not longer going in the I direction, we're going in the minus I direction, and also the point up there is going to be given by y plus delta y up in 2. So I've just written that out there. It's going to be minus f of x at the point x, y plus delta y up in 2, comma z, all times our delta x. I've stuck in 2 delta x's there. Okay, so let's move on, and we'll also look at the right and the left hand side. Now the right and the left hand side, the only component in the y direction, in the j direction, is going to be the y component of our vector function. So if we were then to take the approximation, which is the centre point of the right hand side, well, to get to the centre point of the right hand side here, we're going to have to come along x plus delta x up in 2, and then come up y and z in order to get to that point there. So we've got this value here for the vector function and the y component of it, and then we multiply it by the length of the line, which is delta y, and then we do the same thing for the left component. But you notice in the left component that the direction is no longer in the plus j, it's now in the minus j direction. So we've only got the y component of that vector, and it's minus f of y, and it's at the point, well, it's going to be at x minus delta x up in 2 in order, comma y, comma z, and the length of the line is going to be delta y. So what we do is we're going to add up 1 and 2, and we will add up, so we'll add up the left and the right, and also the bottom and the top. So we start off with the top and the bottom. When we add those two equations together, we take out the value negative, so we'll have our fx at that point there, and minus fx at that point there, times our delta x. Now, we do the same trick here as we've been done in the previous videos when we were deriving the divergence theorems. We can multiply this by a delta y upon delta y, so that will give us the small area element delta s on the top. So then what we can do is we can take the delta x delta y down, and we'll be dividing by 1 upon delta s, and if we take the limit as that delta s, which is just a small area, tends towards 0, then we look at that in terms of the line integral. Now I've been a bit fast and loose here with the nomenclature. I just drew two little lines because we're doing here the top and the bottom, so we're looking at the line integral along the top and the bottom lines of the vector function, and we take the dot product with the tangential component of that vector function. So all we have above here then is our delta y will get subsumed within this here, okay, and we'll just have our delta y delta x is just the 1 upon s here. So whenever we do this limit, we're just going to be left with our minus, they're going to be partial fx by partial y. Okay, so that's the first part of it. Now we do the same thing with the second part. We add in add up the right and the left components. So we add the right and left components, you end up with the fy component of our vector at x plus delta x y z minus fy of our component at x minus delta x upon 2 comma y comma z, and if all times the length delta y. So then we can multiply by delta x upon delta x, okay, and then that means in the top line again we're going to have our little area element delta s. So we divide throughout 1 upon delta s, and we take the limit as delta s tends to 0, 1 upon delta s, and now again we're going round this closed loop, but we're only doing the left and the right components, and we're doing our multiplying our function and taking the dot product of our vector function with the tangential component. So all of that there, then the delta x is going to get subsumed within this here whenever we take the limit, and we're going to have our partial fy by partial x. So finally what we can do is we can add both of these partial derivatives together, then we're going to have the limit round the entire closed loop, and I've drawn that there as a square. So that's the limit around the entire closed loop. So that's going to be partial fy by partial x minus partial fx by partial y. And we can see that this part of it here is actually in the k direction, okay? So we've got the top and the bottom face. The top and the bottom face there is in the Z component. Z is the Z part of it, so it's in the K direction there. Okay, so that would be the normal there and the normal there. Okay, which is in the K direction, and that's the normal to the top and the bottom surfaces. Now we do the same for the right and the left surfaces, and we can do the same with the front and the back surfaces. Now I'm not going to work through all the details, but you can go through yourself, and it's pretty straightforward. I've done it before. I just don't want to clutter the whole entire thing up here. So, but you end up with another set, two other sets of components, the J component and the K component. So this final thing here is going to be another field. Okay, so whenever we find the curl vector field, we get another vector field, and that value, the curl, is going to be given by partial fz by partial y minus partial fy by partial z in I, plus j partial fx by partial z minus partial fz by partial x, and in the k direction partial fy by partial x minus partial fx by partial y. Now this thing here is called the curl of that vector field. So in words we can really say the curl is the limit of the ratio of the circulation to enclosed area as the area tends towards 0. Okay, so it's very similar type of derivation that we did whenever we did the divergence. Now we'll finish this off, and because there's easier ways to remember this and just a bit of nomenclature. First of all, when we looked at the normal component, we defined the normal to the surface, because we could define the normal in either that direction or that direction. So what we do is we use the right hand rule, and if in this instance here, if the direction around the closed loop is in this direction, then the normal is said to be in that direction. So this is a right hand rule. If you take your right hand, your thumb will point in the direction of the normal, and your finger will make a loop in the direction round the loop. Okay. Now also we can see that if the line integral here, which was defined, is the circulation around a path with that normal n, then if the line integral if the line integral, which is the circulation around a path with a normal n, then we can see that this limit is delta s tends to 0 of 1 upon delta s around that same loop of the vector function and the dot product with the tangential component. Well, we can see that whole thing there then is equal to the normal component dotted with the curl. Okay, just another way of writing that out. So what we can do is, in order to try and remember the curl and the different differentials for that curl, we can write it out in determinant form. So we can write out this 3 by 3 determinant. So we're going to have our I, j and our k, and we're going to have our partial by partial x, partial y, partial z. We're going to have f of x, fy and f of z, and we can take the determinant of this. So to take the determinant, it's going to be I times, and it'll be the determinant of these 4 components, and it's j times the determinant of these 4 components, and then the k times the determinant of these 4 components, and you notice actually a minus j there as well. And then we work out the determinants here, so it's going to be, you cross multiply, it's going to be the partial fz by partial y minus partial fy by partial z. Okay, so that's what we've written here. The only thing to note here as well is there's a minus sign here, so it just swaps these 2 round about. But whenever you work through that, again, we get our value for the curl. Now a neat way of writing that there is, we remember that we had the del operator, and we've seen the del operator, there's a video on it a couple of videos ago, and it's going to be our I partial by partial x plus j partial by partial y plus k partial by partial z. So we can see then that we can write the curl as the del operator cross product with our vector function f. Now if you're wondering about the cross product, then there's a video, click on up here, there's a video in the snippet section detailing all information about cross products. So that's really the point we wanted to get to there. Okay, so that gives us the idea of our curl of our vector field. Now here's a simple example, just out of the book that was using there. We had some function x, y and z given by I xz plus j yz minus k y squared. Then to find the curl of that vector field, we write down our determinant here, and then we just work through this determinant. So we're going to have our, in the I direction, we're going to be our partial, it's going to be partial minus y squared by partial y, which gives us minus 2y, and it's going to be our minus our partial yz by z, which is going to again give us our minus y, and then we do the same for the j direction, the j one, and we get the partial by partial x of our minus y squared and our partial by partial z of xz. These two things, xz is going to give us a value of minus x, and the other one's going to give a value of 0. And then finally the k component is going to be the partial of these cross multiplied, okay, which again is going to give us 0 and 0. So whenever we add these two up, we just get minus I times our 3y plus j times our x. So the actual working out the curl is relatively straightforward. It's a nice process whenever you're remembering it via the idea of the determinant. So that's all there is for this video. In the next video, this has been kind of a bit kind of mathsy. It's maybe not kind of a great intuition as to what curl is. So the next video will be a video about an intuitive understanding of the idea of curl. Okay, so thank you for listening, and goodbye.